This is the EdExcel A-Level Further Maths Paper 1, covering the Core Pure content, and this is from the 2022 series. Question number 1. f of z is equal to z cubed plus az plus 52, where a is a real constant. Given that 2 minus 3i is a root of the equation f of z equals 0, for part A we have to write down the other complex root. Well, for part A, we begin by letting the roots of f of z equal 0 be alpha, beta and gamma. We already know one of the roots of f of z equals 0. That's 2 minus 3i. And so what we will do here is we will let alpha equal 2 minus 3i. And because complex roots occur in conjugate pairs, that means the other root, beta c, would equal the conjugate of 2 minus 3i, which is 2 plus 3i. For part B, for the first part, we have to solve completely. F of z equals 0. Well, if we were to solve f of z equals 0, well, we have f of z equaling 0, which means z cubed plus az plus 52 equals 0. And from here, we can see that the product of the roots will be negative 52. And so we have alpha multiplied by beta multiplied by gamma, which is equal to negative 52. Now, we know what alpha is and we know what beta is. So we have 2 minus 3i multiplied by 2 plus 3i multiplied by gamma equals negative 52. 2 minus 3i multiplied by 2 plus 3i, well, we can use the complex feature on our calculator to work that out. 2 minus 3i multiplied by 2 plus 3i, that's 13. So we have 13 gamma equals negative 52, from which we can conclude gamma is equal to negative 4. And so what we can conclude from this, the solutions of f of z equals 0 are z equals 2 plus 3i, 2 minus 3i, and minus 4. Now, for the next part, we have to determine the value of a. Well, as gamma equals negative 4 is a root of f of z equals 0, through the factor theorem, this would imply that f of minus 4 is equal to 0. And so therefore, if I substitute in minus 4 into z cubed plus az plus 52 and set the result equal to 0, from that I can find the value of a. And so we have negative 4 cubed plus a multiplied by negative 4 plus 52. This is equal to 0. And so negative 64 plus 52, that's negative 12. So we have negative 4a minus 12 equals 0. And from that we can conclude a is equal to negative 3. And knowing what the value of a is, we can therefore conclude f of z is equal to z cubed minus 3z plus 52. Now for part C, we have to show all the roots of the equation f of z equals 0 on a single Argand diagram. Well, here is our Argand diagram, and if we plot the roots on, well, we've got 2 minus 3i and 2 plus 3i. We have alpha equaling 2 minus 3i and beta equaling 2 plus 3i. And we also have gamma equaling negative 4. Here are the roots plotted on a single Argand diagram. Question number 2. We have to determine the values of x for which 64 cosh x to the 4 minus 64 cosh x squared minus 9 equals 0. Give your answers in the form q times the natural log of 2, where q is rational, and in simplest form. So we begin with 64 cosh x to the 4 minus 64 cosh squared x minus 9 equals 0. Here we have a hidden quadratic. So if we go to the equation slash function submenu, we can solve this hidden quadratic. We have 64 minus 64 minus 9. We get solutions of 9 over 8 and minus 1/8. And so therefore, if we were to factorize, we have 8 cosh squared x minus 9 multiplied by 8 cosh squared x plus 1 equals 0. And so either cosh squared x will equal 9 over 8, or cosh squared x would equal minus 1/8. But cosh squared x cannot equal negative 1/8, and that's because cosh x is greater than 0. And so we will be solving for x. Cosh squared x equals cosh squared x equals 9 over 8. And recognizing that cosh is the same as e to the power of x plus e to the power of minus x over 2, we have e to the x plus e to the minus x over 2 all squared equaling 9 over 8. And so we have e to the x plus e to the minus x multiplied by e to the x plus e to the minus x over 4 that's equal to 9/8. And if I multiply through by 4 and expand on the left hand side, well, e to the x times e to the x, that will be e to the power of 2x. Then we have e to the x times e to the minus x, that's 1. And then I've got another e to the minus x times e to the x, so that's another 1. So we have e to the 2x plus 2, and then I've got e to the minus x times e to the minus x, which is e to the minus 2x. And this will equal 9/8 times 4, which is 9/2. And if we take everything over to one side, we have e to the 2x plus e to the minus 2x minus 5/2 equals 0. And if we now multiply through by e to the 2x, then we have e to the 2x times e to the 2x, which is e to the 4x. Then we have e to the minus 2x times e to the 2x, that's just 1. And then we have minus 5/2 times e to the 2x, so that will be minus 5/2 e to the 2x. And this is equal to 0. And if I multiply through by 2, we are left with 2e to the 4x minus 5e to the 2x plus 2 equals 0. And so therefore, if we factorize, we have 2e to the 2x minus 1 multiplied by e to the 2x minus 2 equals 0, in which case we can see then e to the 2x is either equal to 2 or 1/2. And so 2x, that's equal to the natural log of 2 or the natural log of 1/2. So 2x is either equal to the natural log of 2 or the natural log of 2 to the power of minus 1. So 2x is either equal to the natural log of 2 or minus the natural log of 2. And so therefore x is equal to 1/2 times the natural log of 2 or minus 1/2 times the natural log of 2. Here are the solutions to the equation. Question number 3. For part A, we have to determine the general solution of the differential equation cos x times dy over dx plus y sin x equals e to the 2x times cos squared x. And we have to give our answer in the form y equals f of x. So for part A, we have cos x times by dy over dx plus y times by sin x, and that's equal to e to the power of 2x times cos squared x. And if we divide through by cos x, that means we have dy over dx plus y times by sin x over cos x, and that's equal to e to the power of 2x times by cos squared x over cos x. And so we have dy over dx plus y times by tan x equals e to the 2x times by cos x. And what we can now do then is recognize that to solve this differential equation we need to use the integrating factor method. And so the integrating factor, that's equal to e raised to the power of tan x dx. So we have e to the power of the natural log of sec x, which is the same as sec x. And so for our solution to this differential equation, we have y multiplied by sec x, and that's equal to the integral of e to the 2x multiplied by cos x multiplied by sec x with respect to x. So we have y times by sec x equals the integral of, now cos x times by sec x, that simplifies to 1, so we just have the integral of e to the 2x with respect to x. And so if we integrate, well, we have y times by sec x, and integrating e to the 2x, we end up with 1/2 e to the 2x plus some constant of integration, a. And recognizing that sec x is the same as 1 over cos x, and if I multiply through by cos x, that means our general solution of y is equal to 1/2 times by cos x times by e to the 2x plus a times by cos x. Then, for part b, given that y equals 3 when x is equal to 0, we have to determine the smallest positive value of x for which y is equal to 0. Well, first of all, we need to find the particular solution to this differential equation. And so, we know that when x is 0, y is equal to 3. So we have 3 equals 1/2 times by the cosine of 0 times by e to the 2 times by 0 plus a times by the cosine of 0. The cosine of 0 is 1 and e to the 0 is 1. So we have 3 equals 1/2 times 1 times another 1 plus a. And from this we can see then a is equal to 5 over 2. And so therefore we can conclude for our particular solution we have y equals 1/2 times by cos x times by e to the 2x plus 5 over 2 times by cos x. This is our particular solution. And so what we are doing is we are finding the smallest positive value of x for which y is equal to 0. So when y is equal to 0, we have 1/2 times cos x times e to the 2x plus 5 over 2 cos x equaling 0. And if I multiply through by 2, we have cos x times e to the 2x plus cos x equals 0. And if I factorize out a cos x from both terms, we have cos x times by e to the 2x plus 5 equals 0. So either cos x will equal 0, or we have e to the 2x plus 5 equals 0. Well, here we can clearly see that e to the 2x cannot equal minus 5 when we solve e to the 2x plus 5 equals 0. It gives no real solution. So we are solving cos x equals 0. And if I work out the inverse cosine of 0, I get pi over 2. So that is the smallest positive value of x. And so the smallest positive value of x is pi over 2. Question number 4 for part A, we have to use the method of differences to prove that for n being greater than 2, the sum of the natural log of r plus 1 over r minus 1 from r equals 2 to r equals n is equivalent to the natural log of n times n plus 1 over 2. Well, for part A, the sum from r equals 2 to r equals n of the natural log of r plus 1 over r minus 1, that is equivalent to the sum from r equals 2 to r equals n of the natural log of r plus 1 subtract the natural log of r minus 1. We use the subtraction law of logs for this result here. And now, if we were to use the method of differences, we substitute in values from r equals 2 up to r equals n and see what cancels out. So when r equals 2, we have the natural log of 2 plus 1, so that's the natural log of 3, subtract the natural log of 2 minus 1, which is just 1. When r equals 3, we've got the natural log of 4, subtract the natural log of 2. When r equals 4, we've got the natural log of 5 minus the natural log of 3. When r is equal to 5, we've got the natural log of 6, subtract the natural log of 4, when r equals 6, we've got the natural log of 7, subtract the natural log of 5. When r equals 7, we've got the natural log of 8, subtract the natural log of 6, and we could continue on. But now what we want is the final two terms in terms of n. So we want the n minus 1th and the nth terms. So when r equals n minus 1, we've got the natural log of n minus 1 plus 1. So that's the natural log of n. And then here we've got the natural log of n minus 1 minus another 1. So that's the natural log of n minus 2. And then when r equals n, we've got the natural log of n plus 1 minus the natural log of n minus 1. So let's see what cancels out. Well, this cancels with this. This cancels with this. This cancels with this. This cancels with this. This would cancel with this, and this would cancel with this. So therefore, what we can see then, the sum from r equals 2 to n of the natural log of r plus 1 over r minus 1, we've got this result being equivalent to, well, I've got the natural log of n plus 1 plus the natural log of n, and then I've got minus the natural log of 1 and then minus the natural log of 2. And so if we were to simplify this even more, what we end up with is, well, using the addition law, I've got n plus 1 times by n on the top. Natural log of 1 is 0. And then using the subtraction law, because I'm subtracting this natural log of 2, I would have to divide n times n plus 1 by 2. And that's exactly what we wanted to show. Now for part B, we have to find the exact value of the sum from r equals 51 to 100 of the natural log of r plus 1 over r minus 1 to the power of 35. We have to give our answer in the form a times the natural log of b over c, where a, b and c are integers to be determined. So the sum from r equals 51 to 100 of the natural log of r plus 1 over r minus 1 to the 35, using the power law of logs, this will be equivalent to 35 times the sum from r equals 51 to 100 of the natural log of r plus 1 over r minus 1. Now what we want really is for the sum to start from r equals 2. And so we would adapt this to say we have 35 times the sum from r equals 2 to r equals 100 of the natural log of r plus 1 over r minus 1, subtract 35 times the sum from r equals 2 to r equals 50 of the natural log of r plus 1 over r minus 1. And so these two lines would be equivalent. And now we can use the result which we found in part A to help us determine this result. What we have then, from r equals 2 to r equals 100, we replace n with 100, so we have 35 multiplied by the natural log of 100 times 100 plus 1 over 2, subtract 35 times the natural log of 50 times 50 plus 1 over 2. So we have 35 times the natural log of 5050 subtract 35 times the natural log of 1275. And this is the same as 35 times the natural log of 5050 divided by 1275, and if we simplify this even further, we end up with 35 times the natural log of 202 divided by 51. So this is our final answer. And so what we can conclude from here then, A equals 35, B is equal to 202, and C equals 51. Question number 5. We are given the matrix M, which is equal to A2 minus 3, 2, 3, 0 for A2, where A is a constant, and for part A we have to show that M is non-singular for all values of A. So for part A, we need to find the determinant of M to begin with. And if we were to find the determinant of M, well, we need to consider the table of signs here. And if we expand along the third column, then what we have is positive, negative 3, and then if I expand along this third column, I cover up this row and then take the determinant of what's left over. So I've got 2, 3, 4, A, and then we've got negative 0, and then if I cover up this row and column, we take the determinant of what's left. So we have A, 2, 4, A, and let's now expand along the final row and column. So we have plus 2 times the determinant of what's left over, which is A, 2, 2, 3. And now we need to calculate what this is. So we have -3 multiplied by, well, here I have 2a subtract 12 subtract 0 multiplied by a squared minus 8 plus 2 times by 3a minus 4. And so if we work out what this is, we have -6a subtract 36 plus 6a, rather here we've got plus 36, subtract 8, and it turns out we get 28. And because this 28 doesn't equal 0, we can therefore conclude that the matrix is non-singular for all A. And now we have to determine in terms of A the inverse of M. Well, our first step is to determine the determinant of M. Now the determinant of M we've already calculated to be 28. So that's what we do for our first step. Our next step is to determine the matrix of the minus, and we'll call this A for now. Now I've set up the matrix, and to determine what goes in this top left, we cover up this column and this row and then take the determinant of what's left over. So I have 3, 0, A, and then 2. And then for the next one, I've got 2, 0, 4, 2. So I've got 2, 0, 4, 2. And then for the next one, I've got 2, 3, 4, A. So we've got 2, 3, 4, A. And then we've got A, 2, 4, A for this one over here. So I've got A, 2, 4, A. And then for this middle one, I've got A minus 3, 4, 2. So I've got A minus 3, 4, 2. And then for the next one, I've got 2 minus 3, A2. So I've got 2 minus 3, A2. And then for the next one, I've got 2 minus 3, 3, 0. So I have 2 minus 3, 3, 0. And then I've got A minus 3, 2, 0. So I've got A minus 3, 2, 0. And then I've got A2, 2, 3 for the final one. So I've got A2, 2, 3. So that's what the matrix of the minus is. And if we simplify this, well, I have A equals, now here I've got 6 subtract 0, which is just 6. Here I've got 4 subtract negative 3A, so that's 4 plus 3A. Here I've got 0 subtract negative 9, which is positive 9. Here I've got 4 subtract 0, which is 4. Then I've got 2A subtract negative 12, which is 2A plus 12. And then I've got 0 subtract negative 6, which is positive 6. Then I've got 2A subtract 12, Then I've got a squared subtract 8. Then I've got 3a subtract 4. So this is the matrix of the minus. And now for our third step, we have to find the matrix of the cofactors. And again, what we need to do here is consider this table of signs. So if I call this matrix C, to find out what this matrix C is, well, I've got plus this matrix 6, then I've got minus 4a, then I've got plus the 9, and then I've got minus 4, and then I've got plus 2a plus 12, then I've got minus 6, and then I've got plus 2a minus 12, and then I've got minus a squared minus 8, and then I've got plus 3a minus 4. So if I simplify this, then I've got 6 minus 4 minus 3a, 9, minus 4, 2a plus 12, minus 6, 2a minus 12, and then I've got 8 minus a squared, and 3a minus 4. So this is the matrix of the cofactors. Our next step would be to transpose this matrix. So if I transpose the matrix, the first column becomes the first row, so I've got 6 minus 4 minus 3a, 9. The second column becomes the second row, so I've got minus 4, 2a plus 12, and minus 6. And then the third column becomes the third row, so here I have 2a minus 12, 8 minus a squared, and 3a minus 4. So that is the transpose of C. Our next step is to find the inverse. Now the inverse of m, that's equal to 1 over the determinant of m times C transpose. So the inverse of m, we've got 1 over the determinant, so that's 1 over 28, and then I multiply this by C transpose, which is this over here. And so the inverse of m is equal to 1 over 28 times the matrix 6 minus 4 minus 3a, 9, minus 4, 2a plus 12, minus 6, 2a minus 12, 8 minus a squared, and 3a minus 4. This is the inverse of m. Question number 6 for part A, we have to express as partial fractions 2x squared plus 3x plus 6 divided by x plus 1 multiplied by x squared plus 4. So for part A, if we begin with 2x squared plus 3x plus 6 divided by x plus 1 multiplied by x squared plus 4, this will be equivalent to some constant a divided by x plus 1 plus bx plus c divided by x squared plus 4. The degree of the numerator is 1 less than the degree of the denominator. And so if we multiply through by x plus 1 times x squared plus 4, we end up with 2x squared plus 3x plus 6 being equivalent to a times by x squared plus 4 plus bx plus c times x plus 1. And we need to find out the values of a, b and c. One way in which we could do this is to substitute in different values of x into both the left hand side and the right hand side. For example, if I substitute in x equals negative 1, then on the left hand side I have negative 1 squared, which is 1, times 2, so that's 2. Then I've got minus 3 plus 6, so that's 5. And on the right hand side, well, if I substitute in negative 1, the bx plus c times the x plus 1 will give 0, and so we are left with a times by x squared plus 4. And with x equaling minus 1, we have 5a on the right hand side. And so therefore, a is equal to 1. Now, let's try a different value of x, such as x equals 0. Well, on the left hand side, I will just end up with 6. But on the right hand side, we have 4a. And then here, we have c times by 1, which is just c. So I've got 6 equals 4 times by a, so that's 4 times by 1, plus c. C is therefore equal to 2. So I've found out what a is, I know what c is, I need to somehow find out what b is. And to find out what b is, we could take a look at the coefficient of x squared. On the left hand side I've got 2x squared, and on the right hand side I have a times by x squared plus bx times by x, so the coefficient of x there is just b. And knowing that a is equal to 1, I have 2 equals 1 plus b, in which case we can see b is equal to 1. And so therefore, what we can conclude then is 2x squared plus 3x plus 6 divided by x plus 1 times x squared plus 4. This will be equivalent to 1 over x plus 1 plus x plus 2 over x squared plus 4. So we have expressed this result as partial fractions, as we see here. For part B, hence show that the integral from 0 to 2 of 2x squared plus 3x plus 6 over x plus 1 times x squared plus 4 with respect to x is equal to the natural log of a times the square root of 2 plus b pi, where a and b are constants to be determined. Well, for part B, we are integrating this result here, and if we use what we found in part A, this is the same as integrating between 0 and 2, 1 over x plus 1 plus x plus 2 over x squared plus 4 with respect to x. Now integrating 1 over x plus 1, that's quite easy, but integrating x plus 2 over x squared plus 4 is a little tricky. So what we can do is rewrite the integral from 0 to 2 of 1 over x plus 1 plus x over x squared plus 4 plus 2 over x squared plus 4. And now each term is integrable. For the 1 over x plus 1 and the x over x squared plus 4, those are of the form f dash over f, and the 2 over x squared plus 4, well, if we go to the formula book, that's of the form 1 over a squared plus x squared, and the result of integrating this is 1 over a times the arctangent of x over a. And so if we rewrite this, we have these terms which are the same, but then we add on 2 over x squared plus 2 squared, where the 4 is the same as 2 squared. And so if we integrate, well, integrating the 1 over x plus 1, that's the same as the natural log of the mod of x plus 1, and then integrating x over x squared plus 4, that's the same as 1/2 times the natural log of the mod of x squared plus 4, and then integrating 2 over x squared plus 2 squared, that's the same as 2 multiplied by 1 over 2 times the arctangent of x over 2. So we are integrating this, giving us the result we see here, and we are integrating between 0 and 2. So if we tidy this up a little, what we have is the natural log of the mod of x plus 1 plus 1/2 times the natural log of x squared plus 4 plus the inverse tangent of x over 2, and we are evaluating this between 0 and 2. So now let's substitute in for our limits. For the upper limit, we've got the natural log of 2 plus 1, so that's the natural log of 3. And then we've got 1/2 times the natural log of? Well, here I've got 2 squared plus 4, so that is a half times the natural log of 8. And then I've got the inverse tangent of 1, because I've got 2 over 2, which is 1. And then for the lower limit, I've got the natural log of 1. And then here I've got 1/2 times the natural log of 4. And then I've got the inverse tan of 0. So if we work this out, I've got the natural log of 3 plus, well, here I've got 1/2 times the natural log of 8, which is the natural log of 8 to the power of 1/2, and the inverse tangent of 1, that's pi over 4, and then I subtract 0, and then 1/2 times the natural log of 4, that's the same as subtracting the natural log of 4 to the power of 1/2, and the reason I'm subtracting is because of the negative here. And then I've got the inverse tangent of 0, which is just 0. So we have the natural log of 3 plus the natural log of 2 times the square root of 2, so that's the same as 8 being raised to the half, plus pi over 4, subtract the natural log of 2. And using the addition law of logs, I've got 3 times by 2 times the square root of 2, and then on the bottom I've got 2, so the 2's here cancel, leaving me with the and then I add on pi over 4 with it. So what I end up with is the natural log of 3 times the square root of 2 plus pi over 4. That's the result of the integral. A is equal to 3, B is equal to 1 over 4. Question number 7. We are given that z is equal to a plus bi, and this is a complex number where a and b are real constants, and for part A we have to show that z multiplied by z star is a real number. Well, what does it mean, z star? That just means the complex conjugate of z. And so for part A, if we have z being multiplied by z star, this is the same as multiplying a plus bi by a minus bi. And if we were to expand this out, a times by a is a squared, and then I've got a times by negative bi, so that's negative abi, and then I've got bi times by a, so that's positive abi, and then I've got bi times by minus bi, which is minus b squared I squared. So the negative abi and the positive abi simplify to 0, and so what I am left with is a squared minus b squared multiplied by minus 1. I squared is minus 1. So we end up with a squared plus b squared. And this result is real, And so what we can conclude then is z times by z star is real. Now, given that z times z star is 18 and z over z star is equal to 7 over 9 plus 4 root 2 over 9i, we have to determine the possible complex numbers z. Well, for part B, I've got z times by z star, which is 18. Now I already know what z times z star is. That's a squared plus b squared. So z times by z star equals 18 would imply that a squared plus b squared equals 18. And if we know that z over z star is equal to 7 over 9 plus 4 times square root of 2 over 9i, well, what this is the same as is a plus bi over a minus bi, so that's z over z star. That is equal to 7 over 9 plus 4 root 2 over 9i. And if I multiply through by a minus bi, that means a plus bi is equal to this 7 over 9 plus 4 root 2 over 9i multiplied by a minus bi. And so what we can do is find out what a and b are by comparing coefficients. So if we take a look at the real parts, then what's real on the left hand side is a, and on the right hand side I have 7 over 9 multiplied by a, so that's 7 over 9 a, and then what else gives me a real term will be the negative bi multiplied by the 4 root 2 over 9i. So I have, if I multiply those together, minus 4 root 2 b over 9 I squared. And so if we rearrange and recognizing that I squared is minus 1, well, what we have then is a equals 7a over 9, subtract, well, I've got 4 root 2 times by minus 1 times by b over 9. So 2a over 9 equals 4 root 2 b over 9. And multiplying through by 9, we end up with 2a equals 4 root 2 b, and so therefore we can conclude a is equal to 2 root 2 b. And recognizing that a squared plus b squared is equal to 18, what we have is a squared, well, I've got a squared, which is 2 root 2 b squared, plus another b squared, that's equal to 18. So I've got 8b squared plus another b squared equals 18. 9b squared is 18. B squared is equal to 2. And so b is equal to plus minus root 2. And now we can find out what a is when b equals plus minus root 2. If I substitute that to find out what a is, well, if b squared is 2, and substituting this into a squared plus b squared equals 18, we have a squared plus 2 equals 18. A squared is 16, and so therefore a equals plus minus 4. And so the possible values of z, we've got z equals 4 plus 4 plus root 2 I, 4 minus root 2 I, minus 4 plus root 2 I, minus 4 minus root 2 I. We've got possible values of z over here, and let's just write them all down. So we have all our possible values of a and b. Question number 8. For part A, given that z to the n plus 1 over z to the n is equal to 2 cos n theta, where n is a natural number, we have to show that 32 cos theta to the 6 is equivalent to cos 6 theta plus 6 cos 4 theta plus 15 cos 2 theta plus 10. So for part A, we begin with 2 cos theta to the 6, and the reason we are writing this down, if I take a look at what I want to show, here I've got a cos theta, so n is 1, and so I would have to raise this to the power of 6, and therefore 2 cos theta to the 6 will be equal to z plus z to the minus 1 to the 6. Now z to the minus 1 is the same as 1 over z. And so 2 cos theta to the 6, that's the same as 64 cos theta to the 6. And on the right hand side, we have to use the binomial expansion. I've got 6 choose 0, z to the 6 times by z to the minus 1 to the 0 plus 6 choose 1, z to the 5 times by z to the minus 1 to the 1 plus 6 choose 2 z to the 4 z to the minus 1 squared, and then I have 6 choose 3 z to the power of 3 times z to the minus 1 to the power of 3 plus 6 choose 4 z squared multiplied by z to the minus 1 to the 4 plus 6 choose 5 z to the power of 1 z to the minus 1 to the 5 plus 6 choose 6 z to the 0 multiplied by z to the minus 1 to the 6. So we have 64 cos theta to the 6. That will be equal to, well here, 6 choose 0, that's 1, so I've got 1 times by z to the 6 times by 1, so that's just z to the 6, and then 6 choose 1, that's 6, so I have 6 z to the 5 times by z to the minus 1, and then 6 choose 2, that's 15, so I've got 15 z to the 4 times z to the minus 2, then I've got 6 choose 3, that's 20, and then I've got z to the 3 times z to the minus 3, and then because of symmetry, next one will be 15 z squared z to the minus 4. Then I have 6 z times by z to the minus 5, and then I have z to the minus 6. And if we simplify this, well, on the left hand side I've still got 64 cos theta to the 6, and here I've got z to the 6 plus 6z to the 4 plus 15 z squared plus 20 plus 15 z to the minus 2 plus 6z to the minus 4 plus z to the minus 6. And so if we group the terms together, I've got 64 cos theta to the 6, and then I've got z to the 6 on the right hand side plus z to the minus 6, which is the same as 1 over z to the 6, and then I've got 6 being multiplied by z to the 4 plus 1 over z to the 4 plus 15 times by z squared plus 1 over z squared plus 20. So now if I use the fact that z to the n plus 1 over z to the n is equal to 2 cos n theta, what we have then is 64 cos theta to the 6, and that's equal to 2 cos 6 theta plus 6 multiplied by 2 cos 4 theta plus 15 multiplied by 2 cos 2 theta plus 20. And so we've got 64 cos theta to the 6 equaling 2 cos 6 theta plus 12 cos 4 theta plus 30 cos 2 theta plus 20, from which we can conclude, if I divide through by 2 on both sides, we have 32 cos theta to the 6 equaling cos 6 theta plus 6 cos 4 theta plus 15 cos 2 theta plus 10. Now, figure 1 shows a solid paperweight with a flat base. Figure 2 shows the curve with equation y equals h times cos of x over 4 cubed, where x is in between minus 4 and 4, and h is a positive constant and x is in radians. The region R, shown shaded in figure 2, is bounded by the curve, the line with equation x equals minus 4, the line with equation x equals 4, and the x-axis. The paperweight is modelled by the solid of revolution formed when R is rotated 180 degrees about the x-axis, and given that the maximum height of the paperweight is 2 centimeters, we have to write down the value of h. So the maximum height that would occur over here, and that is when we have 2 centimeters. And so if we have this length being 2 centimeters, the value of h then, that will be given by h equals 2. For part C of the question, using algebraic integration and the result in part A, we have to determine in centimeters cubed the volume of the paperweight according to the model. Give your answer to 2 decimal places. Well, the volume when rotating 180 degrees about the x-axis, that's given by pi over 2 times the integral of y squared with respect to x in between alpha and beta. And the reason we have pi over 2 is because we are rotating by 180 degrees. And so if we know that y is equal to h times cos cubed of x over 4, that means to find out the required volume, that's equal to pi over 2 times the integral from minus 4 to 4 of y squared, which is h squared, times cos of x over 4 to the power of 6. And so we have pi over 2 times the integral from minus 4 to 4 of h squared, so that's going to be 2 squared, times by cos of x upon 4 to the 6. And so 2 squared is 4, and multiplying that by pi over 2, I get 2 pi. So I've got 2 pi times the integral from minus 4 to 4 of cos of x over 4 to the 6. Now, in order for me to integrate this, well, what I know from part A is 32 times cos theta to the 6 is cos 6 theta plus 6 cos 4 theta plus 15 cos 2 theta plus 10. And if we move this down slightly, what we can say from this line is cos theta to the 6, that's equal to 1 over 32 multiplied by this over here. And so what you'd also hopefully notice is this theta is the same as x over 4. So I need to replace theta with x over 4. And so what I'd have then is 2 pi over 32, because I've got the 1 over 32 which has been factored out, times the integral from minus 4 over 4 of, well, here I've got cos of 6 theta, so that's cos of 6 times by x over 4, and then I have 6 cos 4 theta, so that's 6 times by cos of 4x over 4, and then I have 15 cos 2 theta, so that's 15 cos of 2x over 4, and then I'm adding on the 10. So what we are integrating then is pi over 16 times the integral from minus 4 to 4 of cos of 3x over 2 plus 6 cos x plus 15 times the cosine of x over 2 plus 10 with respect to x. And what this is the same as is 2 pi over 16 times the integral from 0 to 4 of this over here. So rewriting the limits from 0 to 4 means I have to multiply the integral by 2. And so what we have then is pi over 8, and then here what we have to do is integrate cos of 3x over 2, so that's 2 over 3 times by the sine of 3x over 2 integrating 6 cos x, I end up with 6 sin x, and integrating 15 cos of x upon 2, that gives 30 sine of x upon 2, and integrating 10, we just get 10x. So I've got this to evaluate in between 0 and 4. Now, happily for me, I can recognise that for my lower limit, I'll just end up with 0 everywhere. So I've got pi over 8 multiplied by 2 over 3 times by the sine of 3 times by 4 over 2 plus 6 times by the sine of 4 plus 30 times the sine of 4 upon 2 plus 10 times by 4. So I need to evaluate what this is. So I've got 2 over 3 times the sine of, well, here I've got 12 over 2, which is 6. Then I've got 6 sine 4 plus 30 sine 2. And then I also add on to this 10 times by 4, which is 40. And then if I divide by 8 and times by pi, we get 24.564, etc. Which to 2 decimal places, we end up with 24.56. Now, for part D, we have to state a limitation of the model. Well, the model has the paperweight perfectly smooth with a perfectly flat bottom, which wouldn't be the case in reality. Question number 9. For the first part, we have to explain why the integral of cos x with respect to x between 0 and infinity is an improper integral. Well, the integral is improper, and that's because one of the limits is infinity. So we have the infinity as we see over here. And now for the next part, we have to show that the integral of cos x with respect to x between 0 and infinity is divergent. So for part B, if we were to integrate between 0 and infinity cos x, well, we've got this integral being the same as the integral as, well, this is the same as the limit as t tends towards infinity of the integral from 0 to t of cos x dx. So we've got the limit as t tends towards infinity of, well, if I integrate cos, I get sine. So I've got the limit as t tends towards infinity of sine x between 0 and t. So this is the same as the limit as t tends towards infinity of sine t subtract 0, and what we can then say then is as t tends towards infinity, sin t would also tend towards infinity. And therefore the integral is divergent. For the next part, we are given that 4 times by sin x is equal to p times by cos x, where p is a real constant, and given that this equation has real solutions, we have to determine the range of possible values for p. So for the next part, we are given the equation for sin x equals p cos x. Now let's just call this equation 1 for now. Using the definitions of sin and cosine, we have 4 multiplied by e to the x minus e to the minus x divided by 2, and that's equal to p multiplied by e to the x plus e to the minus x over 2. And so 4 divided by 2 is 2. So we've got 2 times by e to the x minus e to the minus x equals p over 2 times by e to the x plus e to the minus x. And if I multiply by 2 on both sides, we have 4 times by e to the x minus e to the minus x equals p multiplied by e to the x plus e to the minus x. So, expanding on both sides, we have 4e to the x minus 4e to the minus x equals pe to the x plus pe to the minus x. And if I multiply each term by e to the x, that means I've got 4e to the x times e to the x, so that's 4e to the 2x. Then I've got minus 4 times e to the negative x times e to the x, so that's just minus 4. And then I've got pe to the x times e to the x, so that's pe to the 2x. And then I've got pe to the negative x times e to the x, which is just p. And now if I take everything over to one side involving an e to the 2x and everything that doesn't involve an e to the 2x on the other side, that means we have 4e to the 2x minus pe to the 2x, and that's equal to 4 plus p. And on the left hand side, if I factorize out an e to the 2x, I have inside the bracket 4 minus p, and that's equal to 4 plus p. So e to the 2x, that's equal to 4 plus p divided by 4 minus p, and so 2x is equal to the natural log of 4 plus p divided by 4 minus p, in which case we see x is equal to 1/2 times the natural log of 4 plus p divided by 4 minus p. Now, as the equation has original solutions, that means that the natural log of the bracket must be greater than 0. In other words, 4 plus p over 4 minus p is greater than 0. Now, if I think about how to solve for p, well, I want p over here to be in between minus 4 and 4. So when p is less than 4 but greater than minus 4, that ensures that the denominator is greater than 0, and it also ensures that the numerator is greater than 0. Which is why the range of values of p, we've got negative 4, which is less than p, which is less than 4. Question number 10. The motion of a pendulum shown in figure 3 is modelled by the differential equation d squared theta over dt squared plus 9 theta equals 1/2 cos 3 theta. Theta is the angle in radians that the pendulum makes with the downward vertical t seconds after it begins to move. For part A, for the first part, we have to show that a particular solution of the differential equation is theta equals 1/12 t times by sine 3t. In other words, we need to make sure that this satisfies this. So for part A, if I have theta equaling 1/12 t times by sine 3t, then I need to show that that fits into this, so I somehow need a d squared theta over a dt squared. So the first thing I need to do is find out what d theta over dt is. And for this I need to use the product rule. I've got sine 3t multiplied by the derivative of 1/12 t, which is 1/12, and then I add on to this 1/12 t multiplied by the derivative of sine 3t, which is 3 cos 3t. And so if we simplify all of this, we end up with 1/12 times by sine 3t, and then I add on 1/12 times by t, times by 3 cos 3t, so that's going to be 1/4 because I've got 3/12, so that's 1/4 t cos 3t. And now if I differentiate again to find out what d squared theta over dt squared is, if I differentiate 1/12 sine 3t, that means I have 3 times by 1/12 cos 3t, and if I differentiate 1/4 t times by cos 3t, well, I have to use the product rule here. I've got cos 3t times by the derivative of 1/4 t, which is just 1/4, and then I've got 1/4 t times by the derivative of cos 3t, which is minus 3 sine 3t. And if I tidy all of this up, well, I've got here a quarter cos 3t and another quarter cos 3t, so that is 1/2 cos 3t, And then I've got a quarter t times by minus 3 sine 3t, so that is the same as minus 3 quarters t times by sine 3t. So that's what d squared theta over dt squared is. And now I need to show that the value of theta 1/12 t sine 3t satisfies this differential equation. So if I substitute in to the left hand side, I've got so far d squared theta over dt squared plus 9 theta. So I've got 1/2 cos 3t minus 3 quarters t sine 3t and then I add on 9 multiplied by theta, which is 1/12 t sine 3t. And if I tidy all of this up, I've got the minus 3 quarters t sine 3t and the 9 times by 1/12 t sine 3t's cancelling out. So I end up with 1/2 cos 3t as my particular solution. And that's exactly what I wanted to show. And now we have to find the general solution to the differential equation. So far I've got my differential equation d squared theta over dt squared plus 9 theta equals 1/2 cos 3t. And what we can do is find out the auxiliary equation by considering what's on the left hand side. The coefficient of m squared is the coefficient of the second derivative, which is 1. So I've got 1m squared, and then the coefficient of m is the coefficient of the first derivative, which is 0. And then for the constant term, that will be the coefficient of theta. So I've got m squared plus 9 equals 0 for my auxiliary equation, in which case we can see m is equal to plus minus 3i. And so therefore, for my homogeneous solution, that will be of the form a cos 3t plus b sine 3t. And so therefore, the general solution to this differential equation, that's the sum of the homogeneous solution and the particular solution. So I've got the homogeneous solution, which is a cos 3t plus b sine 3t, plus the particular solution, which is 1/12 t times by sine 3t. Now, initially the pendulum makes an angle of pi over 3 radians with the downward vertical and is at rest. Given that 10 seconds after it begins to move, the pendulum makes an angle of alpha radians with the downward vertical, we have to determine, according to the model, the value of alpha to 3 significant figures. Well, initially, this would imply that t equals 0, and when t equals 0, we've got theta equaling pi over 3, and because it's at rest, that would imply that d theta over dt is equal to 0. So we've got these conditions which will help us find out the solution to the differential equation, and once we have that, we can find out the value of alpha. Now, because we are given a condition about d theta over dt, that suggests to us we need to differentiate. And so for part B, I would have to differentiate my general solution. So d theta over dt, if I differentiate a cos 3t, I end up with minus 3a sine 3t. And if I differentiate b sine 3t, I end up with 3b cos 3t. And if I differentiate 1/12 t sine 3t, well, I've already found out what that is. It turns out that result is over here as 1/12 sine 3t plus 1/4 t cos 3t. Now let's substitute in our conditions. We've got a condition that when t equals 0, theta is pi over 3. So I have pi over 3 equals a times by cos 0 plus b times by sine 0. Now here, because t is equal to 0, I add on 0. And so what we can conclude from here then is a equals pi over 3. And now, with our second condition, t equals 0, d theta over dt equals 0. Substituting into here, I've got minus 3a, well, I've got 0 equals minus 3a times the sine of 0, and then I've got 3b cos of 0, and then I've got 1/12 times by the sine of 0 plus 0. So I've got 0 equals 3b, in which case we can see b is equal to 0. And so therefore, the solution to the differential equation, now that I know what theta is, well, I've got a cos 3t, now I know what a is, that's pi over 3. So I've got pi over 3 times by cos 3t, and then I have b sine 3t. Well, because b is 0, this term disappears, and so I add on to this 1/12 t sine 3t. So that is the solution to this differential equation. Now I know that when t equals 10, theta is equal to alpha. And I need to find out what alpha is. And so in this case, alpha equals pi over 3 times by the cosine of 3 times by 10 plus 1/12 times by 10 times by the sine of 3 times by 10. So if I work out what alpha is, I have over here pi over 3 times by the cosine of 3 times by 10 plus 1/12 times by 10 times by the sine of 3 times by 10. So I get minus 0.6618, etc. And so therefore, alpha is equal to minus 0.662 to 3 significant figures. Now, given that the true value of alpha is 0.62, for part C we have to evaluate the model. So for part C, the value predicted by the model, which was alpha equals minus 0.662, which is what we found here, that's quite different from the true value of alpha equaling 0.62. And so the model is not good for all values of t. And now, the differential equation d squared theta over dt squared plus 9 theta equals 1/2 cos 3t models the motion of the pendulum as moving with forced harmonic motion. We have to refine the differential equation so that the motion of the pendulum is simple harmonic motion. Well, for part D, with simple harmonic motion, we would not have the 1/2 t cos 3t term, and so for our differential equation we would instead have d squared theta over dt squared plus 9 theta equals 0.